the way it ought to be. So we're going to do lecture by lecture by lecture. Each lecture is a playlist on YouTube, and I finally figured out how to put it all up there and get it right, I think. And I'll apologize right away for the fact that part of lecture 3, a good part, is missing because we had a problem with the SD card in the camera not having enough capacity in it for a quirky reason. And that's fixed. We have a much bigger card now. And then lecture 5 the other day, Tuesday, only got about 15 minutes because the battery died on the camera, but we've got extra batteries now. And for next time, we're going to have a little device that gives us continuous charging through the wall. That'll be good. So today we're going to get into the meat of chapter 5, which is sequencing of peptides and proteins. And as we mentioned the other day, this is used a lot. And it's important with any new protein to get some amount of sequence of part of the peptide, part of a peptide from the protein so that you can find the gene for it and do that sort of thing. So that's what we're going to do today. So we're going to talk about the primary structure of proteins and say, how are they determined? And right at the start, I'll emphasize that primary structure is a synonym for sequence. And sequence is a synonym for primary structure, but don't mix the two. If you say primary sequence, you're being redundant, and you should send that to the Department of Redundancy Department. Okay? So, for further processing. And so the point is, if you say primary sequence, the question you provoke is, what's the secondary sequence? And there's no such thing. And you won't believe the number of times in the current biochemical literature where you will see the term primary sequence abused, okay? Over and over. I found a paper just a couple of weeks ago that did the same thing. It was such an important paper, really neat stuff, great science, and the authors were not careful to say primary structure or sequence. They said primary sequence. Don't do that. If anybody ever asks or ever tells you that they're studying the primary sequence of a protein, ask them what the secondary sequence is, and there'll be a long pause. So anyway, so here we go. We're going to do this. And we note here the sequence of amino acids in a protein is distinctive. Every protein has a unique sequence, we hope. And there are chemical, physical, and enzymatic methods for figuring out the sequence of the protein. So that's what we're going to do. And has this hung up right away? Updates. We don't want any updates. Okay, now we're okay. I don't know why that is. Every time we start now, you have to do that. And I check it actually before we get going, and it still hangs up. Anyway, so you know the story of Sanger and working out the sequence of insulin, what a landmark it was to announce to the world that insulin molecules from one source, human or bovine or whatever, had a unique sequence to them. Well, here's what he found. This is the sequence information that Sanger generated, and you can see the A chain on the top and the B chain on the bottom, and they are linked by disulfide bridges, and you can actually see a couple of interchain disulfide bridges, and there's even one intra-chain disulfide bridge, and that's important. So this is what insulin looks like, but Sanger told us that the B chain, for example, has an alanine, lysine, proline, and so on, and by the way, notice that that's the N-terminus. That's the N-terminus. So this is one of the rare cases where you'll see the sequence turned around. The figure is really meant to be vertical, as you can tell from looking at the names of the amino acids, and then you'd read it from top to bottom. But N-terminus is over here, and you get the idea. But that's the sequence information that Sanger determined. So how do we do that? How did Sanger do it? We're going to walk you through the steps real quickly, and then we're going to go through them in a little more detail. So, determining the sequence, a 6-step strategy, all right? First step is, if there's more than one polypeptide chain, the chains are separated and purified. Sanger had to do that with insulin. He had 2 chains to deal with. He had to separate them first. Why is that? The methods we use are going to look at the N-terminal amino acid, and then the next one and the next one. And if you do that with 2 chains present, you'll get a mixture of information. So you have to separate the chains first. That's the first thing. And then, if there are disulfides, as there were in Sanger's case, you have to separate the disulfide cross bridges, have to take them apart. And there are reducing agents for doing that, and we'll talk about that. And then the third step is you determine the N-terminal and C-terminal amino acids. And you think, why do you do that if you're going to sequence the whole thing? And the reason is, it's a check on your protein before you go through the multi-step sequence that we're going to talk about to make sure that the N-terminus information gives you one amino acid and that the C-terminus information gives you one amino acid. That ensures pretty much that you've got a pure chain, a pure single chain, so that you don't have, for example, two chains with two different amino acids on the N-terminus, two different ones on the C-terminus. So you do a check in step 3, right? And then you really dig in. The 4th step, each polypeptide chain is cleaved into smaller fragments. It turns out that sequencers, people that do this for a living, can only reproducibly do about 25 or maybe 30 amino acids in a sequence before the data just gets so noisy, and we'll talk about why that is. So you cleave the longish protein into smaller fragments, maybe 15 to 20 to 25 residues each, and you sequence each of those. But then you have the Humpty Dumpty problem. What's the Humpty Dumpty problem? Humpty Dumpty fell off the wall and had a great fall and ended up in a whole bunch of pieces, and then trying to figure out where to put the pieces to put him back together is the hard part. If you have multiple segments in a protein, let's say your protein looks like this. There's the C-terminus, there's the N-terminus, and you chop it into 1, 2, 3, 4, 5 pieces. So now they look like this, and you sequence each one, and that's good. How do you put them back together? How do you know this one goes here or this one goes there, and so on? So you have a little bit of a problem that you've created. You've made it possible to sequence each piece by making sure that you don't have anything more than 20 or 25 residues, but then you have the Humpty Dumpty problem of how to put everything back together, okay? And so that's what we'll talk about in the next step, because you repeat step 4 in step 5, but you use a different cleavage procedure, so you get different fragments. So I'll draw little squiggles here to indicate those, okay? So the straight lines and the squiggles are different cleavage procedures. So you start over with another sample of the original protein, and you cleave it again, but with a different set of cleavage points. And then you get overlapping fragments that you can compare and align so that you can figure out the original sequence, and that's step 6, okay? So we're going to walk through these one by one. All right, step 1, separation of the chains. How do you do that? First of all, you say to yourself, the protein is held together either by weak forces only, okay? If there's no disulfide bridges or nothing else strange going on, you've got weak forces holding 2 subunits or 3 subunits or a 4 subunit tetramer or something like that together, all right? And you have to separate those from each other. And you can separate, you can break up weak forces by some fairly straightforward ways. But then if you have disulfides holding things together, you get a more complicated problem. So first thing is, let's assume there's no disulfides. And you can do that with extremes of pH, or 8 molar urea, or 6 molar guanidine hydrochloride, or high salt concentrations. These 2 concentrations of these 2 reagents are classic for protein work, if you will. 8 molar urea is a sufficient concentration of urea that you can do separations of proteins and so on. Proteins fall apart in that. And 6 molar guanidine hydrochloride is the same way. Now, you've met guanidine already because it's the business end of an arginine side chain, right? We talked about how the 3 nitrogens and the central carbon at the end of an arginine are basically, essentially, a guanidine group, okay? Urea, we haven't talked about yet, but you know urea from your earliest days on the planet because you've been urinating it for years, okay? It's true. You don't think about this, but this is what you urinate every single day. A CO with an NH2 and another NH2, and that's urea. That's your body's way of getting rid of nitrogen. We'll talk about that down the road in chapter 25. Okay, we'll say a lot about that. But that's the structure of urea. And that can exist in high concentrations in water, and it denatures proteins, so that's a good thing. Okay? Now, the next step, step 2, how do you cleave the disulfide bridges, if there are any? And you don't know with an unknown protein if you have disulfides, but if you do, you can either do performic acid oxidation, and we'll show you that, or you can use sulfhydryl reducing agents, okay? And so these are the two ways that people usually use. If you use reducing agents, you have a choice. Mercaptoethanol, you need a little higher concentrations, usually 10 millimolar or so, and it's smelly. And so if you work all day in a laboratory separating proteins with mercaptoethanol and you go home at night, your significant other is going to say, take a shower outside before you come in because you're going to smell bad. Or you can use dithiothriotol or dithioerythritol. Those two compounds are referred to as Cleland's reagent after the gentleman at the University of Wisconsin whose name was Wallace, but everybody called him Mo, Cleland, at the University of Wisconsin. And Cleland figured out that you could use DTT, or DTE as they're referred to in their acronyms, to do the same job as mercaptoethanol at only about a 1 millimolar concentration, and they're not as smelly. Okay, so they're better for using lower concentrations and for not being so smelly. But either way, if you use a sulfhydryl reducing agent to break the disulfides into an SH here and an SH there, two cysteines, if you do that, they're going to recombine. So you have to immediately follow your reducing agent treatment with an alkylating agent like iodoacetate. So we'll show you that. Okay, here we go. First of all, performic acid oxidation. Here's the disulfide bond or disulfide bridge. There's performic acid. You should recognize the term per for a per acid, I hope, because formic acid looks like that, okay? That's a carboxylic acid, simplest carboxylic acid you can get, formic acid. If you add another oxygen, you have a per acid, and that's performic acid, okay? And so you can use that, and you can break the disulfides up, and they turn into cysteic acid residues instead of cysteines. So they're SO3 minuses at the ends of the cysteine groups, and so that works fine, and you can stop there. Or if you use an SH reducing agent, like mercaptoethanol, you're going to get a free cysteine like this, and then you have to immediately follow with something like iodoacetic acid or iodoacetate, which will attack that sulfur and give you an S-carboxymethyl derivative. Okay, you should know that from organic chemistry. And you can also use bromylpropylamine. That works just fine too. But these are alkylating agents where the halide, either the iodine or the bromine, goes off as an iodide or bromide, a halide, of course. And the sulfur attacks that carbon and kicks out the halide, or attacks the CH2 up there and kicks out the iodide. So in either case, you're locking that sulfhydryl into an alkyl derivative, and it cannot then go back and recombine to make a disulfide. So use the mercaptoethanol or the dithiothriotol, dithioerythritol, and once you've made SHs out of your SS disulfide bridge, then you treat with one of these reagents or something like it, and you get these, and then it'll stay put and it won't recombine. So that's the important thing to think about with disulfides. If you don't use an alkylating agent, they will just turn back into disulfide bridges again. Okay, so step 3. Now you're going to say, let's make sure we have single chains in our unknown protein that we're going to sequence, okay? So you do an N-terminal analysis, and we're going to show you that you use Edmonds reagent. We talked about that before. And then you get derivatives that are phenylthiohydantoins, or PTH derivatives, right? So you know about that. We talked about that last time. And then you can do the C-terminal analysis a little differently, okay? You use some sort of enzyme, usually, and there are a couple. You can use carboxypeptidase, and looking at the terminology and thinking about that, a peptidase is something that cleaves a peptide, okay? And a carboxypeptidase cleaves at the C terminus. So carboxypeptidase will take the very first amino acid off the chain at the C terminal end, okay? Doesn't do anything here, doesn't do anything through here. It's a carboxypeptidase, so it only cleaves the last amino acid for you, okay? So carboxypeptidase does that, and there's two kinds, and you should know the difference for the first exam and that sort of thing. Carboxypeptidase A cleaves any residue except pro, arg, and lyse, okay? And carboxypeptidase B from pig pancreas only works on arginines and lysines. So think about treating some unknown protein and finding out that